Mic is still working. I kind of have to tilt it down. All right, it's 9 o'clock. We're going to get started. Before we get started, let's all stand up. In yoga class, they would say, set an intention for the day, for the class. You want to expand your brain or learn something new. Try and think of some good questions to ask our speaker as we go along, stuff you're interested in. We're here to learn. We're here to have fun. Here to converse. And thank you all for showing up. Thank you all for being here. So let's just take, a couple breaths just to clear our minds, wake ourselves up a little bit, shake it out. So let's inhale. Exhale. Usually I inhale through my nose, exhale through the mouth. Let's one more time. Inhale. Exhale. Last one. Breath in. Breath out. Nice, nice. All right. So we have a great talk today from Alex. I should have asked you how to pronounce your last name. I'm going to try it. Ciprianovich. Yeah? Wow. Okay.
That's really good.
She hails from Serbia. Got her PhD from the University of Belgrade. She has an about me slide. She'll tell you about herself momentarily. But she works. She's an associate scientist, actually a Wilson Fellow at the lab, which is a very prestigious early career scientist position. I don't know if you know, but like at universities, you've probably heard of tenure track professorships. The lab has a similar sort of path or career development path, and the Wilson Fellow is the first step as a tenure track as a scientist. So she's a big deal. Does a lot of cool work pertaining to AI. Leads one of the AI working groups. They're trying to get more people around the lab to use AI to solve the problems that we're working on. So I won't ramble on too much, but yeah, I'm excited. So let's give it a hand for Alex. Feel free to hop in if you have questions. I'll be monitoring the Zoom for people on Zoom that have questions, and I'll hop in. Let me know when there's time for a break, I guess.
Okay.
Somewhere around halfway, we'll take a 15-minute break. Raise your hand if you have questions. I'll try and pass the mic around to make sure that we can all get our questions asked. Without further ado, you can go ahead.
Thank you. Hopefully people on Zoom can hear me. If not, please complain. I wish somebody gave me that explanation of how the U.S. Career paths work, because again, I'm not from the U.S., so when I moved here, everything was kind of confusing to me. I'm currently leading the Cosmic AI group. That's the official name. So that's everybody who is doing artificial intelligence, machine learning for astrophysics and for cosmology. So the majority of projects happening at the lab are in our group that are astro related. There are here and there some other people in other groups, but we're kind of the main one. But as said, let's see if it will work. Okay, cool. I moved here slightly before COVID. So basically before that, I lived in Europe. I'm from Serbia, and that's where I live. This is this tiny country that's kind of in the Balkan Peninsula near Greece and Italy, so that you can kind of place where I was. And I finished all of my studies, so the whole university, undergrad, master thesis, and PhD over there. And so all of my studies, including the PhD, were astrophysics. And they were more kind of high energy theory oriented. I didn't really do anything like heavy computing inside, and also definitely nothing with AI machine learning, because it just kind of wasn't a thing back then. So there were no courses on it or anything like that. The first course that we had was when I was already working at the university, so maybe a couple of years before moving here. But I've been doing AI for, let's say, last 8 years, something like that. So I kind of got interested in these techniques and learned more or less on my own. and then kind of moved more towards that kind of intersection of astrocosmology and AI. These two buildings, okay, so these two buildings here on top are actually the two buildings where I worked. On the left is my university. So it's astrophysics and astronomy in Serbia are in the Faculty of Mathematics. So I studied with mathematicians and computer scientists and a tiny chunk of astronomers. And so I also worked there, and I worked across the street in this even older building that is like our Academy of Sciences, and there is an Institute for Mathematics over there, so that's kind of where I worked. But then at some point, I started working with people at Fermilab, visited a little bit, and just kind of stayed. So I applied to other positions here and just never left. I really like it here. So yeah, that's kind of my little journey to Fermilab. But anyway, since, as I said, I kind of work at the intersection of astro and AI, that's how I structured this talk. So I am going to tell you initially a little bit about cosmology, and how we came to be and what are the things that we know about the universe. But then in the second part, I'm going to focus a little bit more on AI, what it is, how it works. I'm going to show you some examples that we worked on, so that you kind of get a sense of like how this kind of career track looks like, and also why is AI becoming more and more important in all sciences, so including, I guess, astro. But there are AI people at Fermilab in all groups. So all experiments, everything that we do, even theory, has a couple of people doing something with machine learning. So it's a useful thing to know. In the future, when you start working or get to universities, you're probably going to be using it for one thing or. Okay, so before we start, I do want to make a slight distinction between astrophysics and cosmology. They are used, not interchangeably, but whenever people talk about things, you will hear both words, but they're not really exactly the same thing, because they're trying to look at the universe in a slightly different way. So astrophysics studies particular objects in the universe. So trying to understand the physics of stars, galaxies, black holes, or even the more boring sounding things like dust or gas. You have different types of gas in the universe, and somebody has to understand it, because it does influence other things, even though at first glance it might look a little bit more boring than studying stars or galaxies. So that's astrophysics. And then the cosmology side is slightly different, because it moves away from any specific object and tries to think about the universe as a whole. So cosmology tries to answer the big questions. I mean, even the big questions like, are we alone? So like, how did everything in the universe evolve such that we get exoplanets and other things? Or how did we get here? So how did the universe evolve from its beginning to today? So how did all of the stars get born and evolve, and all of the chemistry that goes on in the universe? And how did all of these components contribute to what we observe today? And of course, all of the extremes of nature. What is dark matter? How does that influence the evolution of the universe? What is dark energy, which is kind of the main cause, and I will, of course, talk about it a lot, so you'll hear more, which is the main cause of the universe expanding and so on. So what is it? What is this force that's causing our universe to evolve over time? How do we study all of these things? How do we try to understand both astrophysical objects and the universe as a whole? Well, there were two main components, but I would say there are now three. So we're using the data from, of course, astronomical surveys and telescopes, but also from high-energy physics experiments here at Fermilab and in other labs on the ground, because they're helping us understand how the world of elementary particles works. because ultimately that's the same physics that happens in space. So both of these components help us get the different puzzle pieces to understand how things work. The other big area are like complex simulations. So you can simulate the whole universe. Basically, you simulate a fake box of a universe and you evolve it over time. So even that actually exists today. And I use these sort of data sets quite a lot. But you can also, of course, simulate smaller things. You can simulate an individual galaxy or an exploding star and so on. And because you know the physics that governs these processes, or at least the majority of it, you can simulate it and compare it to observations and see, is there something that you're missing, basically. But both of these things can produce extremely large data sets. And it's becoming more and more challenging to do even simple things with these data sets, let alone find something new. So I would say that in recent years, in like last decade, AI, artificial intelligence, has helped us tremendously deal with the fact that our data sets are becoming bigger and bigger and more complicated. And it's helping us speed up all kinds of analysis or even just trying to find those weird, unusual things in this big data set. So before we go into kind of the modern world of AI, I do want to start with a little bit of history so that you understand the bigger picture of how we all thought about the universe initially and how it all evolved to what we know today. So one important thing that I always like to start with, which isn't that much about a universe, but at that point, this was like the 5th century BC, so very long time ago. We didn't know a lot about the universe, but there were people who figured out that our own Earth is a round object. So even though there are people even today thinking that it's a flat disk, always remember that there were people 5 centuries before BC that knew that it wasn't. And they knew that from different types of evidence that they saw, like the fact that the ship that is very far away, you start seeing first the top of it because it's kind of behind the Earth, and it seems like it's raising from the water. This is just like one of the things, but they had, of course, other types of experiments that they ran. So when we initially started thinking about the stars and going kind of beyond our own planet, the first thing that people did was just think about the stars as some weird objects that they didn't really understand, but they could observe. And they could also observe that they move around as the year progresses. Of course, today we know that that's because of the rotation of Earth and its own movement around the sun and around its own axis. But at that time, they could just see that the pattern of their movement is very predictable. They could calculate it, that they can say like, okay, these stars are going to be at this specific location in 3 months. And that's going to happen again next year and next year. And these things were very useful for agriculture, for navigation, for boats, and so on. So one of the first big documents that was kind of important for astronomy was actually this Almagest written by Ptolemy in the 1st and 2nd century, where it was a boring document, honestly. It was just a book with a big table with locations for like numbers and locations for stars and how they will move. And people could use that to see where a star is going to be at a particular time and use that for navigation or whatever. The first time, I guess many centuries later, in the 16th and the 17th century, we do have to mention these 2 people, one being Copernicus. You might have already heard about him. He thought that our own sun and our heliocentric system is the center of the universe, hence the name heliocentric, or helios as the sun and centric. So that's what he thought. And maybe it makes sense because what he saw are things rotating and the stars rotating around us. And they're rotating always in the same way, hence we must be in the center. But Giordano Bruno, which is this other guy, said, no, that's not the case. Our sun is one of many. Our solar system is one of many. We are not at the center. We're equally important as everything else. So I think this shift from heliocentric to not heliocentric was like a big jump in the way we thought about things. But as you can see, all of this is still just about positions of objects. We didn't really think about that we didn't think about these objects as something that we can understand, where we can understand physics of them or how they work. The first important names for this shift in the paradigm of thinking about space as just positions of objects to physics of these objects is kind of thanks to Kepler and Newton, because they realized that all of the physical laws, like the gravity, which was a big thing at that time, all of the physical laws that apply here actually apply in space too. So if gravity is pulling an apple to fall down on the Earth, the same type of force must be pulling our own Earth to rotate around the sun and other objects to kind of be in orbit of other massive objects. So this is the time when we start thinking about space in the sense of understanding the physics of it. And so this was, let's see, 17th century. 2 centuries later, 19th. So we are like pretty close to today. We did know a lot more about physics at that time, a lot more. But there was one big mistake that we still kind of thought was true. And that is that the universe is static. So yes, stars move around other objects because of gravity, and on small scales, things move around. But if you think about the universe as a whole, it is static. It just exists. It doesn't, nothing happens to it, doesn't move around. It is just infinite and very still. So this was wrong. The man to blame for the shift of paradigm from this wrong one to the correct one of the universe not being static is, of course, Albert Einstein. But it was, this kind of discovery was even tough for him to accept. So even when he figured this out, he struggled with it. So he published these 2 big papers, and the names of them, or the theories inside, you've maybe heard about: special theory of relativity and general theory of relativity, where he figured out that space and time are not separate. They are connected, and they can affect one another. So that if you, for example, move very fast, or the gravity is very strong, and the space looks weird and curved, your perception of time will change. And that also space and can contract or expand depending on different forces. So he wrote.
Alex, there's a question line to go to rewind the slide or go back.
Okay.
One slide.
This one?
With not a specific question. See? It was just to go back for a second. Good. They said thanks.
Cool.
Maybe
yeah, I mean, yeah. This is a span of many centuries, so we went back and forth many times. But yeah, so in more nearby history, like just a few centuries ago, so this is a cool equation that I'm not going to explain, but the idea of this equation that was published in these papers is that everything here on the left side of this equation represents the shape of the universe or the geometry. And it depends, it needs to be balanced with the thing on the right that describes everything that exists in the universe. So the whole mass of everything, or the whole energy of things that are inside the universe. And as you can see here, they should be equal. in this equation. But it is very hard to make perfect equilibrium. Why would our universe be in perfect equilibrium such that everything in the universe leads to the universe being flat and exactly static? And it was just our chance that we got just enough material inside to make this perfectly balanced. And so he realized that this is very tough to actually happen, and he really wanted the universe to remain static because that's what he knew all his life. So he added this term here in 1917 to be the buffer. So this is a constant that you can kind of invent, and you can invent the value of this constant. You can make it whatever you want such that you balance things out and everything is perfect. And it wasn't until 1931 that he realized that maybe this was a mistake, so that he didn't really have to put it in. He was right initially. The universe is not static. And in the next few slides, you will see why the universe is not static and why he kind of, the way he thought about these things. So if the universe is not static, and I will show you a couple of different experiments and evidence that we know to prove this, then it's a reverse thing, right? It's constantly evolving. And what we know today is that it's actually expanding. So it's becoming bigger and bigger. And if you rewind the time, that means that very, very far in the past, it was, in a distant past, it was much smaller. And if we go to some very distant point, it must have been just a point. So it was like very tiny, and that is the beginning of time and our universe. So of course, today we call this the Big Bang theory. You have for sure heard about it. But I'm going to try to explain like why did we come up with this. Okay, so there's before I go to the three types of evidence that support this theory, I do want to say that Fred Hoyle, this guy here in the 50s, introduced the Big Bang as a term. He didn't know about the whole theory. It wasn't kind of existent at that time. He just wanted a name for something that's separate from the static universe. So how do we call a universe that is expanding and started from something small but isn't static? Okay, the first evidence, maybe the most obvious one, that if I just ask you what would you do to try to figure out what's going on with our universe, you would probably come up with this. Let's observe other objects like galaxies and see how they're moving. Are they moving away from us? Are they moving towards us? What's going on? So this was the first kind of evidence that when we noticed this, we realized that the universe is actually expanding. So we needed to measure the distances to other objects and to see how they're moving. And so the main person for that is Edwin Hubble. You can see him here observing at Mount Wilson. But before he became a professional astronomer, he was studying at University of Chicago. So he even played basketball here. He was born in Missouri, but he actually lived in Wheaton. So that was like right next to the lab. And then I guess moved to downtown so he can go to the university. But at some point in 1924, this is a really cool old New York Times article that actually talks about his discovery. He realized that other galaxies, or at that time we called them nebulae, because they looked like fluffy, fuzzy, tiny clouds that were different than stars. He realized that these nebulae are actually other galaxies. They're not just some weird fluffy clouds inside our own galaxy. They were much more far away, and there are other objects. So how did he figure this out? To figure this out, he actually used a technique that Henrietta Swan-Leavitt figured out. So she worked at Harvard College Observatory, and she was observing these two blobs. So again, at that time, these were nebulae. But today we know these are small and large Magellanic clouds, which are the closest two tiny galaxies to our own Milky Way. They're irregular galaxies, so they don't really look like our own Milky Way. They're just kind of irregular and blobby. But she was observing stars in these two galaxies. And she noticed that some stars, most of them are just the same all the time, but some stars change their brightness over time. And the way they change it is very oscillatory. So they change their brightness like this, and it's always the same. So if one star needs 2 days to change the brightness, it's always going to change it at the same time. So this period for a specific star is always the same. What she also noticed is that the stars, so the stars that had longer periods were also brighter. So this top brightness here is much bigger for those that have large periods. And she could make a plot like this. So you can see here, if the period is on the x-axis, and here it's luminosity or its brightness, the brighter ones here also have the longer period. And these points are actually what she measured. So she saw that this is very easy to just put a straight line through it. What does this mean? This means that if I measure a specific period, like maybe 10 days, I can assume that I perfectly can deduce the brightness of this star. But she saw that this is not the case. Some stars were not as bright, the others were as bright. And this is because of a very simple fact that if you observe something that is emitting light, it's going to be, at least for you, when you observe it, dimmer and dimmer if it's more far away, right? So that's why we call these types of objects actually standard candles. So if you measure something that's dimmer, you can, based on the distance, easily calculate how distant it is because it's dimmer, so specific amount of.
There's one question to, can you go back, I think this 3 slides, I guess, or the slide before this. I think it would be forward.
Can you ask the question and then I will move?
So the question, no, it's I think it might be. Here. Question was about, so one question about the age of the universe. Maybe you can speak to this as you go through. Wasn't there a recent paper that showed that the universe could be double the age we previously thought, by, saying it's 26.7 billion years using JWST data? Is this true or is it still disputed?
Okay, so the paper that he's referring to is the fact that JWST saw a lot more very distant galaxies than what we thought was present at that time. That we don't know why that is. Maybe our models of how galaxies evolve over time are not correct because we just made them based on the data that we saw. It might be that. It might be that it's older and we don't know. So this is really we don't know. It's a weird thing that we are very much excited to figure out why that is. Because JWST could finally observe in a lot of detail galaxies that are really, really, really far away, basically almost the first galaxies. And we'll talk about when galaxies formed and how old the universe is, at least what we currently still think. But it might change. Who knows? By the way, if you have any questions, also just raise your hand so that we can give you the mic and you can. Okay. Anyway, this is a technique to measure distances to these particular stars. And if you observe them, you can observe very easily, you can calculate where they are. And she realized that these galaxies in the small and large Magellanic Clouds are where they are. And the same thing is what Hubble did, but he measured objects in these two galaxies, Andromeda, which is the closest galaxy to us that is spiral, so similar to Milky Way. And this is Triangulum, or M33 as it's. So he observed the same Cepheid stars in these galaxies, and he realized when he measured their distances that they are around 930,000 light years away. So light year is a measure of distance that astronomers use, at least one type of measurement. So it's the distance that a light ray passes through, can like pass in 1 year. So because speed of light is the fastest one that is achievable, that is the distance that a light particle or wave can move in a year. So anyway, what he calculated was this amount, but he knew even before that was known that the Milky Way is 9 times smaller than that. So if these stars in these galaxies are 9 times more distant than the size of the Milky Way, obviously these things are not inside our own galaxy. They are separate objects, but very distant ones. So nebulae all of a sudden became other galaxies. And so all of a sudden our tiny Milky Way universe shifted outwards. Now we knew that we can actually see things that are. But he needed one more thing. So he now just knew the distances to objects. This is not enough for you to figure out if things are moving away from you or not. So he couldn't figure out that the universe is expanding just yet. For that, he used a different thing that you experience every single day, which is the Doppler effect. So the Doppler effect is the effect of stretching or squishing any kind of wave. In this example, it's a sound wave, but it can also be a light wave. When either you are moving as an observer or the object that is releasing the sound wave is moving with respect to you. So you can experience that when you have a car that's on. If it's stationary, you just have a very constant humming sound that is coming from it. But if it's going to pass you, as it comes near you and more closer and closer, it becomes more kind of high pitched, right? And then as soon as it passes you and starts going away from you, it again becomes duller and duller and more stretched out. And the same thing happens to the light from galaxies. And we can use this fact to see if the galaxy is moving away from us or towards us, or it's just ending. So this is a very small but, and I guess, easy formula to figure out, but kind of boring, where the frequency of the sound that is emitted, so f0, actually what you observe, which is this green f, depends on the speed of the observer and of the source, as I said. So if either of these two things is moving, you as the observer are going to observe this green f as something different from what the source is actually emitting. So for galaxies, we have to think not, again, about the sound waves, but about the light waves. And you can measure something like this. We call this galaxy light spectrum, which is the amount of light at the different frequencies. It doesn't look as nice as this, but this is basically kind of how it looks. And we also know that there are some gaps in this spectrum. These gaps happen, they're called absorption lines. They happen because atoms, any kind of atom that exists, likes absorbing light. But it likes only light at specific given frequencies that it particularly is fond of. That is because different atoms have electrons at different energies, and when they absorb light, these atoms actually electrons absorb them and move around in the atom. So if you have, for example, a hydrogen atom, you know exactly where you should expect these lines for a hydrogen atom. Hydrogen atoms are great in space because they're the most abundant. So usually these lines from a hydrogen atom are the brightest ones that we can observe. And I want to show you how this actually looks like back then. So this is Vestas Slifer, who actually observed these things for different objects. You can see like Virgo, Ursa Major, Corona Borealis, and so on. These are the objects that he observed. These boring looking lines are actually these spectra that are not very colorful. But what you can see is these two gaps close to each other. These are two lines from the hydrogen molecules. And you can see that for every object here, you can see these two gaps. But they're at different locations, meaning these galaxies here are moving all at different speeds because this particular thing is moved to the different location. But one thing that is interesting also is that it always moves to the right, or it always moves to longer wavelengths, or we call these longer wavelengths are actually shifted towards red colors. So what we actually call this effect is redshift. So basically, this redshift can tell you how quickly is this galaxy moving away from you. And as you can see, everything that he observed was moving away from him. Nothing was moving towards him. So Hubble basically used the same technique to calculate the speed of galaxies that he measured distances to. So he could make a plot like this, where the distances are measured using Cepheid stars, and the velocity is measured using this redshift effect. And again, you see kind of a good way of fitting this with a line. So he basically said the velocity is equal to some constant that we now call Hubble constant times the distance, meaning the more distant objects are moving away from us at higher speeds. So first, everything is moving away, so the universe must be expanding. And second, the things that are more far away are also moving away faster. And please don't think that this is because we are the center of the universe. I always like showing this raisin bread as an example. So if raisins inside of bread are galaxies, if you started baking this bread in the oven, it started growing and becoming bigger and bigger. All of the raisins, right, inside the bread would see all other raisins moving away from one another. So there is no specific central raisin or more important raisin. So for the raisins, the space or the bread is expanding equally everywhere. This is the first evidence. There is an extra thing regarding this evidence, which is much more current. This is this thing that you can see here is not a normal star. It's still a star, but it's an exploding star called Type 1a supernovae. It always explodes at exactly the same time, meaning it is, you can see that initially there are two stars here, the tiny one and the big one. The tiny one is pulling the gas from the big one, and when it reaches a specific mass, it always explodes because it becomes unstable at that time. So if you find these objects wherever they will always explode with the same energy, meaning you can still use them as standard candles, just like stars. And you can just see, okay, I saw this explosion. It's not exactly as what I calculate it should be bright. So I can calculate how distant it is, right? Because it's distant, hence the light drops off. And you can measure things that are much more distant with these stars because they're 5 billion times brighter than the sun. So you could measure galaxies that are absurdly more distant from us than what we could before. So these three guys did that. And they even won the Nobel Prize for it in 2011. So they made a plot like this. All of these are supernovae that they measured. And they said, okay, if the things that we measure are in this blue area, that means that the universe is accelerating. If the things are here in the red area, the universe is decelerating. And if they are perfectly aligned here on the diagonal line, the universe is statically expanding, expanding at the same rate. And as you can see, most of them are kind of more towards blue. So the universe is accelerating, not by crazy amount, but it's still accelerating. And for that, they got a Nobel Prize. Yes, so the other two evidence are related to much earlier times. So I have two more things to cover, but let's go to the question.
Well, it's a interesting question is how you think about it cosmologically, but the question is, do we know where the center of the universe is?
Again, as with the raisin bread, there isn't a center because every point is equally important. So the space itself is expanding, and there is no preferential point. Any other questions?
Was there at one point a center of the universe, like right after the Big Bang?
I mean, at the point where it appeared, let's say, at that point, it was just as now, but ridiculously small. So at that point, there wasn't a central point. Before that, it didn't exist. So you have to think about it as you're thinking as if you were an entity outside of the universe. So if you were looking at the universe and you can see a blob and you're outside, you would say, okay, there is obviously some center. But if you're inside, there is no center for you. So imagine that you are a 2D being that doesn't understand the third dimension, and you live on a ball. And you cannot see up or down. Your whole world is 2D, the surface of the ball. For you, there is no center. There's no preferential point. For us, as like some other 3D beings, of course, it looks different. But for the person being inside the space, there is no center. You can kind of think about it that way. Other? Go ahead.
So do you think it's possible that our universe could actually be like some four-dimensional shape that we just can't comprehend?
It is. It is possible. It could be whatever number of dimensions we. So I don't know a lot about this because that's not my area of research. But like string theorists, they think about 11-dimensional space. So why not? It's just that for now we don't really know.
Someone on Zoom asked, or about the shape of these dimensions. Is the universe flat or spherical in shape?
It is flat, but that's kind of what we know from evidence. It's not really like curved, but the expansion isn't constant. It's expanding more and more, but the shape of it, let's say, is.
Questions?
We have time to cover the second one. The third one quickly before. Okay. The second one. The second one are related to observations of something called the cosmic microwave background. This is actually, these are observations of the earliest thing we could ever observe in the universe. Believe it or not, we can very much observe it. But there is a whole interesting, fun story of how this came to be and how we can like now really observe it in a lot of like detail. So let me try to explain first what is this cosmic microwave background. So to do that, I need to show you the universe. So show you how it all evolved. So let's say that at some point, the Big Bang happened. After that, really quickly, so all of these initial things that I'm going to talk about are happening within the first second after the. So this is like 0 and 43.43 zeros, and that's after the Big Bang. So the universe was extremely hot initially, and something called inflation happened where it expanded really, really rapidly, but just for a brief, tiny part of a second. After that, and look at this here, we're still within the first second, so just a bit later. It cooled down enough so that the forces that we now know exist could start doing its thing. So they could start existing, let's say. So the first thing that started like existing is gravity, but then also we have the strong force holding the nuclei together, and then weak electromagnetic force. So the universe started becoming, because these forces started existing, the universe started creating particles. But the particles that could be created are the more fundamental, simple ones that are building blocks for more complex things later on. So things like quarks or photons and neutrinos, the tiny things. They needed the universe to cool down a little bit more so that they can combine and make more complex things. So initially, they were just bombarding each other, hitting, and creating matter and antimatter. So antimatter is just a flipped version of our own universe where like protons are negative and electrons are positive. But somehow a little bit more of matter was created, and hence everything that was left in the end was matter. Because matter and antimatter, when they collide, they annihilate and just make energy. So anyway, matter won, and now this is the first time that I'm talking about the moment after the first second. So a lot of things I had to explain, but this was still within the first second. So after like 4 seconds, things cool down even further. So you could make the first elements, elementary particles that make nuclei, so neutrons and protons, and okay, electrons as the thing that goes around the nuclei, but it was still too hot for them to actually combine and make atoms. So you had nuclei separately from electrons, and they were just like kind of bumping into each other, but nothing was happening. They needed, again, the thing to cool down even further. And when this happened was in between 2 and 20 minutes after the Big Bang. So the universe became cold enough to form some of the first elements, like hydrogen, deuterium, which is just heavy hydrogen, helium, and a tiny pinch of lithium. But electrons are still kind of free. And because of that, all of the energy and all of the photons that are created in this crazy mayhem of collisions are always absorbed by something else. So electrons couldn't really freely traverse the space. The first time when they could actually do this was when electrons truly combined with nuclei to make atoms. And believe it or not, so this happened much later, at 300,000 years after the Big Bang. So this is the moment where we finally can see photons. So because the photons were finally free, this is the first moment where we can actually observe. Before that, everything is dark for us because there's no evidence for us to observe because no photon was able to escape. So when we observe, the first thing that is possible to observe in the universe is these first photons. And you can see that this happened a lot later than the Big Bang itself. Of course, you needed millions of years to first form stars and galaxies. So we needed a lot more waiting to do. And then 9 billion years later, solar system forms. We form here. And then today, at least at the moment, we believe the universe is 13.77 billion years. So let's go back to this moment where we could observe the first light. This is what the cosmic microwave background is. So the universe was very hot at that time. It was at 3,000 kelvins. So kelvins is just a unit of measuring temperature that scientists use. It's pretty easy to convert to Celsius. It's just around 300 degrees different. And you can easily also convert it to Fahrenheit. But 3,000 Kelvin, anyway, is really, really, really hot. Okay? So these two guys are the people who actually measured it first, even though they didn't know it. Penzias and Wilson had this, they worked in New Jersey in Bell Labs, and they had this weird thing that was actually a radio antenna. So it is pretty much like how radio works now. It is picking up on radio waves, very long wavelength waves. What they noticed is that whatever they did, wherever they turned the antenna to, they always saw this weird background noise. This background noise was actually a remnant of a signal that has 2.7 kelvins of, I will show you why in the next slide, of temperature. And it was actually the cool down version of these 3,000 kelvins that were initially released. But they didn't know it, of course. They even thought that maybe pigeons, because they were like nesting inside, the pigeons were causing this background noise. They cleaned everything out, and I mean, they realized that it was still there, even when the antenna was clean. The way we figured this out, what this is because of the theorists. So Robert Dicke, who works in Princeton, he realized that he knew about the Big Bang theory. He knew that the first light was released at 3,000 kelvin. And he realized that, okay, if so much time passed and also the universe is expanding, we should see this light now as like a background noise, but at way lower temperatures. So you can actually, I don't know if any of you have ever seen in real life these kind of old TVs, but when I was a kid, this is how TV kind of looked like. Okay, I mean, slightly more modern, but this part was the same. And if you didn't put any channel on, you can see like this noisy background. And part of this background is actually some of these photons causing the background are actually the first. So even though I didn't know it and nobody really like thought about it, you kind of were looking at space. But for this thing that where they figure out that this background noise are these first photons, Robert also got a Nobel Prize. So let me show you how these observations actually looked like. So let's first look at this plot. This plot shows the measurements that was done at that time with the first telescope, let's say. And you can see it perfectly fits this line. And what is this line? This line is something that we call a black body radiation, meaning when you have a perfectly black body, like theoretically perfect, it will emit light of exactly this shape, and the shape, or like where the peak of this distribution is, depends only on its temperature. So if you perfectly measure this, you know what is the temperature of this body. And this corresponds to 2.75 kelvins. This was actually the most precise measurement ever made at that date of anything in physics or anywhere else. So they were very sure this is 2.7 kelvin. How it looked like initially, as I said, with this antenna that they had, everything was 2.7 Kelvin. So this is observation like of the whole sky everywhere. And as you can see, everything is kind of the same color, which in this case represents 2.7. The only thing you can see here slightly brighter is this horizontal line, which corresponds to our own galaxy. After that, we realized we want to measure this a little bit better, see if this is indeed so flat. So we launched COBE, the telescope that observes also at the same wavelength, but in space. And we can see that it wasn't as flat as we thought. Still, the brightest thing is our own galaxy, but you can see that there is some variation over here. And the variation was kind of, we could add another zero. So we could observe variations of an order of a magnitude lower. Then we launched WMAP. We got even lower. And then today we have Planck. These measurements are even more precise. And you can see like very, very small variations. And actually the variations that we observe here are like this small. So 1, 2, 3, 4, 5 zeros and 1 of a Kelvin. If I just want to make this comparison to show you like how detailed this measurement is. So if the Earth's surface was as smooth to 1 part in 100,000 as this error here is, the highest mountain on the whole Earth would just be 100 meters or 300 feet tall. So these are measurements that are extremely precise. Because of that, we can make a plot like this that observes how correlated are these variations on different scales. So on small scales, we plot here. On tiny scales, we plot here. On huge scales like this, like how correlated are these things when they're very distant is here. And yeah, this is basically today used to better constrain the temperatures and to understand the temperatures in the first universe and to understand this moment when the first photons were released. So I have a very brief third evidence, but because it's 9:54, I think I'm just going to leave this for after the break, and then we go to any questions related to the number 2.
Well, there's one question. It's a little, might be, I don't know if there's one in the room.
There is one in the room.
So I guess one about the conditions of the early universe is asking about I think I see in textbooks that some forces like separated out at different times. Like the question is like, did some forces emerge earlier than others? Like was gravity the first one to emerge?
Yeah. So that depends on like what kind of force it is, what is its strength, and how, like, the distance where it operates. So it needs different type of, let's say, temperature to exist. So yes, gravity detached first, then, as I said, the strong force, and then the weak, and then finally the weakest of them all, electromagnetic. But yeah. Okay.
So when you talked about the very early, like, unobservable part of the universe, because it's unobservable, how do you know that the expansion happened at the time scale that it did? How do you know what happened at under 1 second and then 4 seconds? Like, how are you able to distinguish that?
This is thanks to theorists and thanks to like other like properties of like high energy nuclear physics that we understand. So everything related to how particles interacted, or how they when they appear, when they could exist and when they couldn't, is all thanks to high energy physics theorists and our understanding of how particle world works. And then the really quick expansion. We know that from observing, for example, the first photons, because we see that there are no interactions and no correlation between things that are very far away. It looks like at some point things separated enough so that things that were more distant from one another couldn't like really influence one another. So kind of from that, you can deduce that something like that maybe happened. Okay, who was next? I think you were next, and then we have two.
Hello? Oh, there we
Okay,
go.
cool.
Okay, so was the universe at the time of the Big Bang like perfectly smooth, and why isn't it today?
Depends what you think of smooth. Like when you say the universe was smooth, the like the space itself, we can say that it is smooth, like on large scales at least. This thing that is not smooth is the content of the universe. So when particles started existing, of course, they were individual entities, and hence they were not, like, of course, perfectly homogeneously distributed in the space. They could move around. And when the photons were captured the first time, they kind of reflect where these atoms were located at that time. So there were places, of course, where you had more atoms or less atoms, just because they were just chaotically moving, right? So these fluctuations are really tiny. So overall, you could say it was kind of smooth and homogeneous, but not really, because there were these tiny overdensities and underdensities. And this is actually one of the most important things, because if things were perfectly smooth, we would not be here. But because it wasn't perfectly smooth, you had places where you had a slightly more matter. And because of that, the gravity could pull other matter to coalesce with the overdense regions. And hence, over time, you could create galaxies and stars and other things. If everything was perfectly smooth, nothing would move anywhere, and you would just have separate particles floating and nothing would ever. So we're kind of lucky that this happened.
So my question was related to like the first evidence, and so due to the like the acceleration caused by like the dark matter, some parts of the edge of the universe are moving faster than the speed of light. So would it be possible to utilize that to move matter, like other matter, faster than the speed of light?
I mean, I guess we don't know how we would do that right now. But if we could, that would be really awesome. Because currently, again, I always remember the idea with the balloon and the 2D person on the balloon. So the 2D person couldn't really figure out how to utilize something outside of its own universe. So hence, in the same way, we like don't really know how we could utilize that. But I also don't think that, like, I feel like theorists could come up with something at some point. It's just.
Do we know how fast the universe expanded during the inflation period, like right after the Big Bang in those first couple, like within the first second?
I mean, no, I can't tell you the number or anything like that, especially because like, how do you, what it was? We just know that it's like vastly bigger and more than anything that happened right after that. So yeah, I guess yes and no is the answer. Not really, but we do know from some evidence that this happened. Okay, so we have one more very brief, well, it's not brief, but I'll cover it briefly, evidence for the Big Bang theory. And as you can see here, it's about something we call primordial nucleosynthesis of the elements. So this is actually connected to this time of the first 2 to 20 minutes, where we actually made, so the nuclei, the protons and neutrons combined to create the first nuclei and first elements. So yeah, so it's related to the evidence of how many of these first molecules actually formed at that time and why. So, okay. So the person that we need to think for this kind of discovery and these studies is David Schramm, who works at UChicago. And he was studying these first elements. And so what he realized, you see them, okay, is that, again, because of our knowledge of nuclei and particle physics, we understand what kind of temperatures and pressures and generally environment, how would that affect the production of these first elements. So theorists could basically make a plot like this, where they would say, I guess you can, the x-axis is how many baryons or like particles making these protons and nucleons and so on compared to photons, which depends on the temperature. So basically the x-axis, you can also think of it as a temperature. So how many, depending on the temperature, how many nuclei of, for example, helium-4, if you look here on top, how many nuclei can we form? And this is a theoretical line. So basically, if you can measure the temperature of a specific period, you can say, okay, I can produce this amount of helium-4. These other lines are, this one is for lithium, and these two are for regular, also for helium, and this is for deuterium and hydrogen. Because we could measure the CMB, right, that I talked about before, we knew what the temperature was, well, 100,000 years later, but let's say around that time. And from that, extrapolate what would be the temperature at the moment when these nuclei were formed. And this is what this horizontal line gives us. Okay, so now we know what the temperature was at that time. How do we measure if what we assume was made at that time was actually made? How can we do that? Well, we can do that by observing the amount of these elements in the first stars. So the oldest stars, the most distant ones that we can observe. Why? That is because the first stars were made from the elements that were around, right? So the amount of hydrogen in them or helium and other elements will need to reflect the environment. So whatever was available at that time. And these yellow boxes that you can see here, this is the big one, the big one. These are big because the error bars on this measurement are very big. But you can see a very tiny box here. This is because the measurements for deuterium and helium and hydrogen are very small. And these are the measurements in first stars. Meaning you can see like this one, although with big error bars, overlaps with what we assume should be there. This one too, right? So he had multiple different elements that were matching the predictions from the Big Bang. Hence, this was a good evidence that the theory was good. And obviously, you can see that lithium is very much not correct. This is called the lithium problem. And this is something that is still not solved. So this is something that, at least partially, I was studying in my PhD. You can see that the measurements in first stars are lower than what we think should be there. So we think it should be somewhere over here, or actually over here. Right? This is because, well, we don't know why, but overall, another interesting thing about lithium is that everything in the universe destroys it. So it's very easily destroyable. So everything in stars or anything else that happens, all of the processes basically destroy lithium. So all of the lithium that's around, more or less, is the primordial old lithium from the Big Bang. And so all of the lithium that we're digging up on Earth and making into, putting in all of our Teslas and other cars and phones and other things, all of this lithium is the Big Bang lithium. So this is kind of, I don't know, for me, a mind-blowing kind of piece of information. But anyway, if we disregard this mystery, all of the other ones that are also more, like the processes that make them are clearer to us, and all of those match what the theory says. So for now, this is a good evidence that the Big Bang and how we think the universe evolved is still okay. We just maybe need to figure out what's happening later or something like that that's causing this discrepancy for lithium. But as I said, all of these are just different pieces of the puzzle for us to understand that the universe is evolving. And as I mentioned at the end of the previous hour, is because there were these small inhomogeneous regions of where the particles were initially, over time, gravity caused things to evolve and coalesce in these sort of filamentary structures. So this is a simulation of a fake box of a universe that starts from almost homogeneous particles, but not really, just like we had at the CMB time, for example. And if you just put in gravity inside, it will form these filaments. And this is exactly what we see when we observe on large scales the universe. So this is kind of how, on large scales, the universe looks like. So let's move on to how we're studying the universe today, and what are these new techniques and the learning part that I mentioned. How is this helping us understand how things are evolving and galaxies are and how they look like? Again, I always like to start with history so that you can understand why we're talking about this. So the way we studied astrophysics and astronomy evolved over time, obviously, because the first thing that we could do when we started observing stars is build simpler, smaller telescopes. This one is, I mean, it's not that old, but it's from the last century. This one is actually from my hometown. And you could observe really cool things with it, but you couldn't see very far, right? We then realized we needed to go into orbit, and we needed to launch things in the space so that we can remove the effects of our own atmosphere that is obscuring the faint stuff, right? We also realized that if we wanted to build things on Earth, we needed to go bigger. And bigger isn't always achievable because it's not possible to build it, or it's extremely expensive. But we realized that at least for some types of telescopes, we can actually build arrays of them. So these are radio telescopes. So you can see many similar antennas. And they actually, when you combine them, combine information from them, it is the same as if you have built one ginormous telescope that has the same size as all of these, like if it was just one big. This is, of course, much better, much more, I mean, cheap to build, and you probably wouldn't even be able to. But with all of these telescopes, we were able to make surveys, so observations of the universe wherever we look, so the whole sky, everything that is visible, in different wavelengths. And these are, again, some different examples of our universe at different wavelengths. Again, as before, with CMB, you can see the horizontal line, meaning our own Milky Way, as the brightest thing that you can see in any wavelength. But you can also see other objects and other interesting things happen. So we have all of these big data sets that are very complex, but there is another progression that is very important here, which is how the computing evolved over time. So when we made the first computer in the 60s, these were not very powerful. I mean, compared to your phone now, was just ridiculously simple. But they were huge. They weighed tons. They filled entire rooms. And basically, you had, if you're somewhere very fancy at a really good university or a company that built it, you would have one huge computer in a room, and everybody at that university or company or whatever had to use this one computer. So it was one computer for hundreds of people or thousands of people. And plus, you really couldn't do that much with it. But just 20 years later, we figured out how to make all of the components in the computer much smaller so that we can fit them into a small packaging and make it also much more cheaper so that everybody can buy their own personal computers. So it's just 20 years, basically. So this is evolving really, really fast. And of course, 20 years after that, you already have really tiny computers, and everybody can buy multiple computers. You have one in your laptop, on your phone, or whatever. You had many computers per person. And then finally today, you not only have your own personal ones, you have computers in your cars, in your washing machines and fridges. They are communicating with one another. But not only that, you have even more powerful computing that belongs to, for example, big companies that you can use if you're doing research or something that requires a lot more powerful computers that you cannot own on your own. You can either for free or pay to use it. So you have computers that are extremely powerful at your disposal if you need them. And the fact that today we have first big complex data sets, but also have developed the computing to those lines that we can actually really use it in a useful way on these big data sets is the reason why today the AI era is kind of blossoming. But before we go more into the AI stuff, I do want to, again, explain three terms, because at least for these, I'm sure you have heard them many times being used very interchangeably, but they're not, if you really think about them, they're not exactly the same thing. So the biggest term here is artificial intelligence. It encompasses all of the methods and all of the computer programs that you can write that will mimic some kind of intelligent human behavior. But these do not really need to be anything special. They can be really tiny pieces of code that do things exactly as you want them, so that you can write, if you see X, do Y. So there is nothing smart happening there. You are the person writing the code and making it behave a human would. But these are all hard-coded tasks. Subset of that would be a bit more fancy, which would be machine learning algorithms. They are very different because the way they achieve this human-like behavior, they achieve it by training from examples. So which is the paradigm that how you all learn to do anything. You learn from examples. So your parents showed you many images or whatever, real dogs and cats, and told you these are cats, this is cat, this is cat, this is dog 1 million times, and then you as a baby knew how to recognize a new dog or a new cat when you saw them. So you learn from examples. And machine learning algorithms basically learn in the same way. So this shift in paradigm, how things are made, is what is fancy and what is like really cool and interesting. Again, a subset of that would be deep learning algorithms. They, again, learn from examples, so that is the same. But the algorithms themselves are slightly more complicated, and they use something called neural networks. There is a plethora of different types, shapes, sizes, types of neural networks, and these are the things that I will mostly cover and show you some of the basics of. More history, but this is a fun history that I don't know. I really kind of find it fun when I like learn this. So Chicago is an interestingly good place for both computing and physics. And if you look through history, many important things have happened. I don't know, I'm proud to be here, I guess, and contributing to what's going on today. So in 1943, McCulloch, which is the older guy here, and Pete on the right, started chatting. So McCulloch was a professor at University of Chicago, but his field was neuroscience. So he was a person doing biology, medicine. Pete, at that time, believe it or not, was just a high school student, actually a high school dropout, but but he was really good at math. Anyway, he was extremely good at math. And they started talking about the brain, about neurons, and about how human brain works. And so this is a real like neuron in your brain. So it has like 3 parts. It has these dendrites here that gather electrical signals coming to it, and they process them in some way in like this main part of the cell called soma. And then once that is processed, they forward via this axon, they forward the information to the synapses that connect to the new cell. So they gather electrical impulse, do something with it, forward to the next one, and then the next one will do this. Of course, as a simple cell, this is a very simple process, and you can very easily think about it in mathematical terms, and that is really what they talked about. And they actually published a paper at that time. It wasn't very popular then, but it's kind of the interest in it skyrocketed later on. So they realized we can write how neurons work in mathematical terms. Let's make the electrical current numbers, so these x's are inputs. Let's make the cell a function that does something to these numbers, and then let's forward the output to the next such entity, like an artificial neuron. And just as real neurons, one cell cannot do very much, but if you combine thousands of them, you can do a lot. And so only, again, in really very brief time, in 56 already, people started thinking about it so much and trying to build code that could do really interesting things. And so in this Dartmouth conference, they actually established artificial intelligence as a research field. So this is where, like, they said officially, okay, this is going to be the name of this. But, you know, they couldn't really, for a very long time, again, due to computing, lack of funding and other things, they couldn't really do many very fancy things with it. They could do bits here and there, but not really what scientists really wanted. One really cool algorithm in the 80s was this neocognitron, where they realized they could make a computer understand shapes by cutting the shape into simpler parts, such that you have like the first layer of this program that understands only vertical and horizontal lines. And you can combine this information into more complex parts, and then you combine this into more complex ones until you basically, by like a puzzle, understand the whole shape at the end. And this is kind of the logic of how deep learning algorithms work with images today, although in a more complex way, but still the logic, like the how it works, is kind of there. One very important person in the name that you should remember is Jan LeCun. He is still a huge name in the AI industry. And he built, in the 88, he built something called a convolutional neural network that was able to automatically, just in the similar way like this neocognitron, understand written digits, so that it can automatically scan checks in the post office or in banks, and so that you can make this machine where you put in your check and it automatically scans the numbers, knows where to put money or to withdraw money from. And so even today, like, these algorithms are being used basically everywhere to do these things automatically. But this is when it all started. Still, like, again, the computing part, like the computers weren't really there yet, so that you could do anything like bigger than that. You could read digits, but these are like simple images. You couldn't do much more than that. Things kind of skyrocketed in 2012 because of Alex Kryzhevsky, who was a PhD student at that time. He was a computer science student, and he was learning how to program on GPUs. So these are the graphical units that you have in your laptops that run video games or anything video related. They are a lot more powerful than CPUs and a lot faster because they needed to be developed to process all of the stuff in the video game. So he was just, in general, he had a course on how to program for GPUs. And he realized, well, now I know how to rewrite code for GPUs. What if I rewrite something like Yann LeCun's CNN, but to run on a GPU? Then I could do it much, like, I could run it much faster. I could do probably many more complicated things with it. And he actually did that in his own computer in his dorm room. He decided to enter this ImageNet competition, which was a competition that ran every year where people wrote any kind of code that they wanted. And the goal was to classify, there were these tiny images that, I mean, they're really tiny here, but these are all different images here. And you had hundreds of classes, and classes were like boat, car, cat, dog, whatever, other different animals, objects, and things like that. And the idea was make a program that can classify this data set to the best possible accuracy. People, I mean, were okay doing that, but it wasn't really good. But when he made his own, he called it AlexNet, his CNN, and trained it in his own dorm room and sent them the model, his accuracy was much better than anybody has ever done and so he automatically became like super famous. And the paradigm that we could do machine learning and AI on GPUs helped us develop a lot more complicated, better algorithms that do now many much harder things with this ImageNet. So, but you can see that like basically the whole craziness was started in 2000s, not before that. Sure, we had many really cool things before that, but there were really substantial limits for what we could do. So why is AI in general important for us in astronomy, but I think this applies to the whole science. So before the AI age, if we wanted to study any kind of object in space, we would usually need to write down an equation that describes some physical property. And if we wanted to study a galaxy, we had to make approximations that are very substantially, well, they were very severe. So like you couldn't write an equation that describes such a complex galaxy. You would have to say, okay, this galaxy has a spherical shape, and let's calculate all of the properties that it has, assuming it's a sphere, which it is not. Or if it's a spiral galaxy, we would say it's a disk. But you were basically throwing away information because we couldn't handle the details, right? But with AI, especially AI that works, for example, with images, all of a sudden you have something that can handle the details. You can handle all of the information that's in the image, and you can build models based on all of the data. So it also is very good at handling large data sets and once you train your model on examples, you can really quickly apply it to any new data. So it accelerates research. It helps us build models based on the data and all of its intricacies. It helps us with unexpected discoveries and saying like, oh, this looks weird. It's not like all of the classes that you showed me, for example. And it also doesn't care how complex the space of the problem is or the data set is. It can work. It's not limited by 3 dimensions as we. But how does it work? The building block of a neural network is that artificial neuron that was invented in the 40s. We also call it a perceptron. And here it is again. It looks the same as before. It has some x's, which are input values, so in some numbers. Or we can look here. We have weights, which are some trainable parameters, which is how the model learns. So these are also numbers, but these start as random values. And as you show your model more examples, it fine-tunes which weights should it multiply these inputs with. Then we sum that all up, And we go through some activation function, which can be something like the step function or something else, some kind of function that changes the output sum to some other number. This is a very important part because it adds some nonlinearity, and only because of this nonlinearity, we are able to combine hundreds and thousands of neurons into one system that can actually learn something complicated. If you only have the input layer and one layer of whatever size you want of these artificial neurons, and you give the output out, we call this a shallow neural network or a multi-layer perceptron. But you can always stack more of these. So the simplest possible extension to this is just have more layers. They're the same, but have more of them. We call these deep neural networks, and these are the simplest possible but powerful types of algorithms that, of course, are just the beginning. There are many, many other types of deep neural networks. One specific type of neural network that I work with a lot, and a lot of astronomers do, are those that work with images. So that don't work with like individual numbers, but with 2D matrices that have numbers in them, but they actually mean something to you when you look at them, their image. There are three main types of problems that you can do and tasks that you can do with images. First one, you can do classification. So you can say, train a model to say this is an image that has a dog in it. Then the more refined version would be detection. So not just say there are dogs in this image, but put a bounding box around each example of this dog in the image so that you know the location. And the most refined one out of these would be segmentation, which is tell me exactly which pixels in this image belong to the dog, which pixels belong to the background or the stick or whatever. So basically, it's kind of like a classification of each of the pixels. So classification per pixel. Okay, how do these work? Because I just want to show you a little bit how do they look and how the process of training them looks. So you have examples, but as I said, when you were kids, you needed these examples to be labeled in the most simple case. So you needed, for example, if I'm studying galaxies, I need a lot of galaxy images that also have associated label called galaxy. And then maybe I need a lot of other images that have stars in them, and I have associated label stars, so that the model can start to recognize how galaxies look like versus how stars look. These examples with the labels go into this neural network, and then the network outputs a prediction for a given image. So it sees a new galaxy and predicts, okay, this is a class galaxy. So how does that work? So let's say that I have this image of a galaxy. How do I actually get information from it? So this is now, it looks slightly more complicated than those simple neural networks. This is how these convolutional neural networks look like. So these are the networks, as I said, that Alex was using for the ImageNet competition, that Jan LeCun was using for the digits, and that we are now using for whatever we want for galaxy image. As you can see, first you have a couple of rows of 2D layers that are layers that are there to scan the image and get some information out. And only after a couple of these layers, you squish them into 1D layer, and then you can do something that's more familiar to you from like the few slides ago, where you have neurons stack in 1D layers, and you use them to output the numbers for predictions for these classes. And in theory, so you can see that these are just numbers. These are just numbers. So if I train my model correctly, it should output the highest number for the correct class. So initially, it was just going to predict random things. But the more examples it sees, the better it becomes. And over time, it should predict the correct galaxy class, in this case, as the highest number. So these three areas do different things. So the 2D part extracts features or properties from images that we will use later to figure out how to classify things. The fully connected dense layers with neurons, separate ones, do the classification. They use this information to connect and train these weights that I was talking about, such that it predicts the correct class. And the output is just a probabilistic distribution saying this class is more likely than the other one. So how does the 2D part work? So you have to remember always that no matter how fancy the processes that AI can do are, there's still very simple algebra behind the whole thing. So if you think about the image as a 2D matrix of pixel values, maybe those are zeros and ones only, for example, to simplify things, you can create a smaller matrix that we call a filter, like this yellow one, that you slide across your image to scan and extract useful information. And when you scan it, for example, you scan one 3x3 area, you get some number out, and you write it in a smaller matrix, like this red one. You can repeat the same process over and over as you go deeper into the network. And so that you can understand what this scanning does, it extracts maybe horizontal lines or vertical lines or whatever other property that this filter can extract. This is how it gets extracted. And let me show you how that really looks. So this tiny thing is the filter. It's a tiny matrix of zeros and ones, and you can see the black and white as like where the zeros and ones are. And when you scan it, this image with a different filter, you get different properties being enhanced. So one will enhance maybe vertical lines, one will enhance diagonal line. So you kind of break up this complex image into a subset of different kinds of feature maps and information. Okay, yes. So this is, for example, how that would look like for digits. So the first layer sees things, you can see it highlights like diagonal line or something like that. These different ones represent different filters that we scanned. As we go deeper into the network, as I showed you, you reduce the size, so things look less pretty and less meaningful for us. So things are more and more pixelized, but the information is still there. So basically, in some way, you're summing up this whole information into a smaller patch. So yeah, so that the output is hopefully the one that you want. Okay. We don't have much time, so I will just go to some astro examples that I can show you what we do. So of course, as I said, you could do many complex things, even make the robots work. The AI is doing this, just these algorithms are slightly different and more complicated than the ones that I showed you. But in astronomy, you can see these are the number of papers that are being published with machine learning and AI in the title. And you can see that the numbers are really skyrocketing. We're using them for classifying objects or inferring properties. We use them to help us speed up simulations or help us scheduling observations or even automating observations or making these robots for Mars or whatever rover that we want to do things more automatically. But I'm going to focus with an example on this top one, just to show you how useful this is. So these are the studies that I've done with, I guess now almost 3 years ago, with a PhD student, Dimitrios Anoglidis here, the top plot. And Alex is he was his primary advisor for his PhD. He works at UChicago and he works also here at Fermilab. So we were studying a type of galaxies that we call low surface brightness galaxies. These are, you can see them here on the left, very not interesting looking galaxies. They're extremely faint. They're actually fainter than the night sky. So before very recent times and before this survey, dark energy survey, we couldn't even observe them. We needed really good telescopes and we needed them to observe very long time so that these faint objects can actually kind of pop up from the background and you can actually observe them. Interestingly, they are probably the most abundant type of galaxies. So all of the galaxies that we saw until very recently were not really the majority. And we really need them to understand the evolution of galaxies and also how the dark matter, for example, influences the evolution of galaxies. So when we made these observations, somebody had to make a catalog of them so that people can study them. And so initially, poor Dimitrios had to sift through thousands and thousands of potential candidates that some other simple automated algorithm extracted for him. But that algorithm also extracted weird things like these artifacts on the right, which you can see are parts of other faint objects, or a star is there, or something blurry. So you actually have to spend months and months of your life and just look at these images and figure out if something really is a galaxy or not. So ultimately, he had 400,000 candidate images to look at, and out of that, he found 40,000 images. So just 10% of all 400,000 that he looked at were actually these objects. And with new telescopes, and even with this one, with the next set of observations, we're going to have more and more and more. And at some point, you would need to hire an army of students to do this, and you would still probably not be able to finish it. So it's not like we just want to use AI, we really have to use AI because we need to do this process much faster. So he trained a similar CNN, like those that I talked about, and he used the catalog that he made as an initial starting point to teach it to distinguish between artifacts and real galaxies, and this is what he got. So these colors here show what the CNN thinks is the most important pixel. So you can see that when it sees a galaxy, it's looking at the galaxy, and when it sees an artifact, it's looking at the artifact. And based on that, it decides what is what. Oh yeah, and I mentioned dark matter, so I will say just briefly because I really didn't mention it at all. It's a tiny digression. It's tiny digression that I do want to mention. So how did we even start thinking about dark matter and what it is? So we had to first figure out that it exists. So this guy, Fitzwicki, is the first person that's important for that story. So he observed galaxies in this group or cluster that we call coma cluster, and he realized that galaxies are rotating around some central point in this because they're connected by gravity, but they're rotating really, really fast. And that if everything that he sees in the cluster is the only thing that the cluster has, so all of the stars and galaxies, they should be catapulted out with those speeds. But there is additional gravity there holding the galaxies together that we don't see. So him being Swiss and talking in German, he called this dunkle Materie, or dark matter. So this is kind of where this term originated. Other important person is Vera Rubin here on top, who did the same type of observations, but within galaxies. So she observed how stars in spiral galaxies rotate. And she made a plot like this, where this on the x-axis, you have distance from the center, and on the y is the speed. And as you can see, the speed just increases. So basically, all of these stars should be catapulted just like those coma cluster galaxies if the amount of matter that you see is all that there is. So the gravity holding the stars together is not enough for these speeds. Hence, again, the galaxies themselves must be embedded in some dark matter halo that has extra mass that we don't see. And actually, dark matter there's more of it. So we believe that there's 25% of dark matter in the universe and only 5% of regular one that you can see. And all of the rest is dark energy, or the energy that we, again, don't know what it is, that is causing the universe to accelerate. So this is the digression. I have 4 more minutes, right? So I have more examples, but I do want to ask if you have questions, because that might be more fun than others.
So when you guys are looking at images of galaxies, you guys usually, like from JWST or such, you guys usually encounter images that are low clarity or sometimes might be very blurry. Do you guys use AI to clarify those images, or do you guys just kind of leave them be and don't do anything with it?
This is a good question, because if we're doing some kind of studies, and especially if you want to measure a property of a galaxy, we usually keep them as they are because we don't want to change them and not be sure that we change them correctly. But hopefully in the future, I think we're gonna be doing more of what you suggested. There are papers already like published that are actually trying to do that. So maybe you have old telescope that has observed a lot of galaxies, but they are not very nice, like they're blurry. But then you have a new telescope that only observes part of the sky, and you have the same galaxies, but much better. You can use the pairs of the bad one and the good one to teach AI to translate from the blurry ones to clear ones. And this has been done really successfully so far. But as we're scientists, we're kind of conservative, and we're always scared, like, okay, it looks correct, but what if something tiny is not correct? And then we're scared of like deducing any physical properties from that. So this will happen eventually, but the progress is slow just because we want to be.
Time for one more. I see a hand.
So are there still occurrences of like possibly where the AI can't tell if it's an artifact or not?
Oh. Absolutely. So, I mean, AI is definitely not perfect. I mean, it's going to be as good as the training set that you make. So if you have a weird one that really isn't represented in the training set because it's a weird one, it might be wrong for it. But of course, so for many cases, we do this with AI first, and then somebody might look at those and clean if there is something like really wrong in there. So yeah, it's definitely, these things happen.
Nothing else? Maybe no hands. Well, we can thank the speaker for a very nice talk.
Thank you.